saying that you, ideally, to get this optimal coverage, they would need to train F and G together. However, for the purpose of this paper, you're given F, and then from F, we want to find this G, this rejection function. So the problem is find G given F, a confidence level delta, and a desired risk R star. So you find a G whose test error is no larger than R star with a probability of 1 minus delta. And this would be, so, okay, so this is the kind of problem setting. I'll be writing some of the equations down just so we can just keep track of everything. Okay, so you have X as your feature space, so yeah, for example, raw image data. Then you have Y, which is a finite set of labels. And F is your classifier, so X maps from X to Y. And first thing we've got is our true risk, which is so you have your probability distribution of X and Y, and then your true risk is the expected loss function. Yeah, the expected value of your loss. So that's why I wrote on the board. Maybe it's a bit bigger if you can't see. And your loss function could be, in this case, I think throughout the paper, unless specified otherwise, past a certain point, it's the 0-1 error. So if it's true, if you've got it correct, 1, otherwise 0. And you have a labeled set SM, which is your X, Y pairs. So that's M. You have a basically data to train on of X and M X Y pairs sampled IID from the probability distribution. So now we can see that you can calculate quite easily the empirical risk. So highlighting horribly, but you have the empirical risk is 1 over M times the summation of the loss for each sample in your training, your labeled set, which is your training data. Right? Well, and the aim is to produce a selective classifier, so more formally. And you have your G selection function, which is you want to find this FG pair. So that's basically it, right? You want to find if your Gx equals 1, so you just classify it with your classifier, and otherwise don't know Gx equals 0. So, and from there we can get this selective risk. So this is how we would evaluate our selective classifiers. So on the top it is the expected. There's a way. So you have the expected of the loss of f of x to y times gx over the coverage. So firstly, we can look at the coverage. The coverage is the expected gx. So you can think about the coverage as how much, what percent does it know. So if the coverage was 0.5, your selective classifier would only classify 50%, half of things from your probability distribution, Pxy. So that's your coverage is literally coverage, how much you can tell. And so here we have the selective risk, which is if you notice that the loss is times by the g of x term. So when the g of x term is 0, as in the classifier is abstaining, you don't consider those. So you can think about it as the expected loss of everything you are able to classify divided by the coverage. So you can already see here there's a trade-off where you can trade off the risk for the coverage. So if you just look at the denominator and then so yeah. And what you are trying to do is this: given a classifier F, a training sample M, confidence parameter, and a desired risk target, our goal is to basically satisfy this. So the selective risk, the probability that the selective risk is greater than your target risk is less than delta, which is your confidence parameter. So, and out of all the things that satisfy that, you want to find the G that can give the most coverage. So I don't think it's too crazy. So yeah. And here they're going to go into the algorithm for how this works. So you have so you're given a so based off a classifier F, you can make a confidence rate function here, K of F. So you can interpret this as, so if K so if you have K of K of x1 is greater than x2 for 2 of the feature space, then you know that you interpret that as the confidence about x2 is no higher than the confidence about x1. So it's basically a measure of how sure you are about the input you are classifying, and what this function would actually look like is discussed in the next section. But for now, just going to talk about how you can build your G, your rejection function, based on this. So it's simply saying that your G is going to be defined as if your confidence about the input is above a certain threshold, so that's the top case there, you return 1, 0 otherwise. So that's, I think, quite straightforward. I mean, try me at any point if it's not. And like we had the empirical risk, we can also make the empirical selective risk. So by just basically summing up the terms from I to M and then dividing it by M. So you have the empirical selective risk is you divide it by the empirical coverage, and that's all the samples that you didn't abstain from predicting the average loss among them. So here we're going to go a bit to the algorithm. So the algorithm it performs a binary search to find the optimal bound guaranteeing the required risk, so you input R star with this sufficient confidence. So just to go straight to the algorithm. So this is probably the most important part. So the first line of line 2 actually is to sort the data according to the confidence on the samples. So you would you just sort it according to your confidence rate function. Then you keep your bounds